This is lecture 11G, and it is just a list of useful and important power and Taylor series. In these expansions, some important things to note are these even and odd symmetries, or rather sometimes it's a lack of symmetry, and also note the behavior of the polynomials near x equals 0. The first Taylor series that I'm listing here is the most important one. In fact, almost everything follows from it. This is the expansion for e to the x. And here it is in a compact form, and the terms look like this. And you can see they're very easy to remember. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc. And this series converges for all x. For all values of x, it converges to the values of e to the x. I'm going to list the remainder here, but there's no sense in me reading that. Here's a graph showing e to the x. E to the x here is in red. That's e to the x function right there. The blue line is just second order. That means there's only two terms to the Taylor series expansion. Of course, the more terms you use, the better agreement you get in the interval of convergence. And here, of course, it does converge everywhere. So this was second order using two terms. Let's try third order using another term. Alright, you can see that it seems to have overshot for x equals 0. Here, it was too low. Right. And now let's try the fifth order. The fifth order, that tail's kind of coming down a little bit here. And on this, for x greater than 0, the values are now approaching a little bit closer to e to the x. More terms gives you better agreement. Now we have the expression for sine x. Here's the sine of x. Whoa, sorry. Okay, so here's the sine of x again after the program jumped around a little bit. Here's a Taylor expansion for the sine of x. 1 minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Note its similarity to e to the x. So here's e to the x. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. Alright, now for sine x, it's very similar. Of course, you don't have these even terms. Those are gone. And then you have the signs are alternating. But you can see a similarity. You're dividing by the factorial. Factorial equals the power of x. Of course, you know what cosine looks like. It again has the alternating terms, but it has the even terms. In red here, let me get the pen. In red is the sine of x. The blue line is a first order approximation. This is your linear approximation. It's pretty good agreement right here, but that's about all that you get out of it. Right. The seventh order approximation is much better. Right, that's shown in green. Of course, the more terms, you get a better agreement, or you get agreement actually further out, further along along the sine curve. This expansion is valid for all values of x. In other words, that series expansion converges to the values of sine of x everywhere. Right. I mentioned at the beginning of this lecture that it is very useful to look at the behavior near x equals 0. So near x equals 0, if you look at that series expansion, I'm going to have to go back to that now just to show it to you. So what we want to look at is the values of, for x close to 0. Alright, if x is close to 0, then x cubed, let's say, pick any number you want, 10 to the minus 6, obviously x cubed is very, very small. X to the fifth is even smaller. So you can, if you neglect these very small numbers, for small values of x, the sine of x is approximately x. And you see that from the series expansion. These higher order terms are very, very small and they can be neglected. And that's what's written here on this slide. For absolute value of x approximately equal to 0, sine of x is approximately equal to x. Often this is said in terms of angle. For small angles, for angles much less than 1, sine of theta is approximately equal to theta. And that is sometimes, so you can replace sine theta by theta with a certain amount of error, but it's not too bad. You can see that from that series expansion. That's one a good approximation for theta, for the sine of theta, for theta approximately 0. And now let's look at the cosine of x. Remember again, e to the x. The expansion for e to the x was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, let's give you one more, over 4 factorial, etc. The sine of x was the x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Well, you see all these odd powers here? Of course, that makes sense. Sine is odd. Now look at cosine. Cosine is even. What do we see here? We see even powers. The signs alternate, so again we have these alternating signs, but we have even powers with cosine x, the odd powers with the odd powers with the sine of x. How about the behavior when x is approximately 0? When x is close to 0, again we have the higher order terms, x squared, x to the fourth, x to the sixth. Those can be neglected, and for x approximately equal to 0, cosine of x is approximately equal to 1. If you say this in terms of angles, for very small angles, the cosine of theta is equal to 1, approximately equal to 1. Remember, for sine, for small angles, for small theta, I'm sorry, the sine of theta is approximately theta. For small theta, the cosine is approximately 1. Here's the expansion for the arctangent, oh, missed the highlighter, for the arctangent of x. Looks a lot like the expansion for sine, except that these denominators are just 3 and 5 and 7. They're not 3 factorial, 5 factorial, 7 factorial. So it actually looks pretty similar. Near x equals 0, similar. This is similar to the sine function. The higher order terms can be neglected, and the arctangent of x is approximately equal to x when x is approximately 0. Or for angles, for small angles, the arctangent of theta can be approximated by theta itself. And here's a graph showing the arctangent function and second, fourth, third, and fourth order expansions. Now the arctangent function is not like the sine, cosine, and the exponential. Sine, cosine, and exponential expansions converged everywhere. For the arctangent function, the series expansion converges for absolute value of x less than or equal to 1. And that's what's being shown here. You see, the closer you get, the more terms, you're seeing a convergence here to the, in red is the arctangent function. Now let's look for at values of x greater than 1. If you remember from the previous slide, we were working right in this region here, right? And the higher order terms, for higher order terms, the graphs approached the arctangent function. Yes. Now let's look at what those second, third, and fourth order terms are doing when x is greater than 1. We know it doesn't converge. I just wanted to demonstrate it here. Right. Almost unable to see it is the arctangent function right there. and look at how large these values are. Second order, it looks like it's getting worse and worse and worse. Third order peels off fairly fast, and the fourth order is even faster. So what we're seeing here, instead of these higher orders, you put more and more terms together, seeing a convergence to the values of the arctangent function, we're seeing that these do indeed diverge from the arctangent function. So this is a good demonstration here. In this region, the arctangent function converges. As we add more terms, going from sixth to third to fourth order, we see the graphs coming into the arctangent function. When we look at this region where the arctangent function, the series expansion does not converge, we see the second, third, fourth orders diverging away from the arctangent function. I'm just mentioning a few others of the series here, a few of the power series and Taylor series expansions here. Here's a natural log of 1 plus x. Note its similar. Whoa, that was unnecessary. Okay. Note its similarity here to e to the x. You're seeing alternating signs, which you don't see in e to the x. The denominators are not factorials as they are in e to the x, and you're missing the initial 1. Also, this only converges for this half open interval from -1 to 1, less than or equal to 1. The next two series are versions of the geometric series. They converge for absolute value of x strictly less than 1. We have here 1 over 1 minus x and 1 over 1 plus x. It's easy to see how to get from one to the other. Let's look a little bit at this convergence. So we have the Taylor series for 1 over 1 minus x. It converges for absolute value of x strictly less than 1. Again, the red is 1 over 1 minus x. You see, as we add more terms, here's the third order. This one's the fifth order. We see the series expansion converging to 1 over 1 minus x. And this is true only in this for x less than, strictly less than 1, or greater than, strictly greater than -1. What we looked at before were analytic functions and their series representation. Some functions have only a series representation. One of them is the Bessel function. The Bessel function is seen in heat conduction problems, things with cylindrical symmetry, plates, okay, where you're just trying to study heat conduction problem in two-dimensional plate. The Bessel functions arise in such problems in physics, and they're denoted like this. Let me get the pen. They're denoted with a J. Then they'll have a subscript. Here's J0, here's a J with a 1. That is the Bessel function. The J means the Bessel function, and this is the order. Order 0, J1 is the Bessel function of order 1. You don't even say the J, you say Bessel function instead of J. You look at the J and say Bessel function. And then Bessel function of order 1, Bessel function of order 2, etc. I'm just presenting them here just so that you can get an idea that some functions have only a series representation. Here's a representation for J0, okay, Bessel function 0, and here's a representation for the Bessel function of order 1. Right. Slight difference in the series expansion. These converge everywhere, and I'm going to show you a plot of them next. You could apply the ratio test to see that they do indeed converge everywhere. And here are some graphs of the Bessel function of order 0, 1, and 2.